Uh, okay, it's a lovely evening today, and welcome everybody to the seminar of Alexandre Belin from CERN. And he works on many exciting things, and so we were asking him to either give a talk on his eigenstate thermalization hypothesis in CFTs. He has worked on that, or some other recent work, and he's going to tell us today about bootstrapping quantum extremal surfaces, of understanding how to compute them from CFTs. And so over to you, Alex, then, to tell us about it.
Great. Thanks a lot, Anne, for the very nice introduction, and thanks for the invitation to speak at the seminar series. It's my first seminar I ever give in India, unfortunately online, but it's still great to be here with everyone. And so today I'll tell you about some work that came out recently, say in the last 2 months, but it's really part of a longer program. So mostly my talk will be based on a paper from July with Sean Colin Elrin, who's a really excellent grad student at UC Davis and who's applying for postdocs this year. So you should definitely have him on your radar. But like I said, it's part of a longer program that we started also some years ago. And I'll mention some earlier work with Nabil Iqbal, Sagar Lakande, and Yuri Krudov that came out, say in the last couple of years. And let me just start by making 2 disclaimers before we get started. The first one is, please interrupt me and ask questions as much as you want. Basically to first order, there's never such a thing as too many questions. So don't hesitate, especially online. It's really important to get a feel of whether people are following or not. So please interrupt me. The second one is some aspects of the results that I'll discuss are slightly technical and have, unfortunately, kind of ugly expressions with many gamma functions. And I'll try to simplify them as much as I can, and I won't always write the arguments of gamma functions and that kind of thing. But if you get confused, again, just stop me and ask questions, and I'll try to say exactly what's going on, but I'll try to simplify things as much as I can. Great. So let me get started. Oops, got my pen. So in the last 15 years, we've really learned a lot about quantum gravity and holography by using insights from quantum information theory. And the star player in this program has really been the Ryu-Takenagi formula, or its generalizations, including quantum corrections, which is the following. It's a formula to compute entanglement entropy in conformal field theories and holographic conformal field theories of some boundary region A. And I'm sure you've all seen this formula by now. It's given in terms of, it's a kind of generalization of the Bekenstein-Hawking formula for black hole entropy. And it's obtained by computing the area of a certain surface plus the bulk entanglement entropy of all propagating quantum fields on some bulk space-time. Okay, so here's a cartoon of how this works. There's some bulk spatial slice here. And we're going to specify some CFT, region A. And then you're going to look for surfaces, gamma here, that are homologous to A, compute their area, and also compute the entanglement entropy of all fluctuating fields that are here on this background. They could be, fluctuating gravitons, fluctuating scalar fields. And then what you're supposed to do is extremize the value of this generalized entropy for all choices of surfaces gamma, and you find the special surface that extremizes this generalized entropy, gamma extremal, which is called the quantum extremal surface. And okay, so this formula has really been kind of like the star player in this whole program, and it's a formula that can be derived as first done by Lefkovich and Maldacena, by the semi-classical gravity path integral. By the semi-classical. Is there a question?
Oh, no. I think it was just
Somebody forgot to turn off their mic. No worries.
Exactly.
Okay, and there's been very exciting progress in the last, say, 2 or 3 years. And one thing that was able to be shown is that if you try to compute the entropy of the Hawking radiation in an evaporating black hole, and you use this formula, you can reproduce something called the page curve, which is a curve compatible with unitarity. Okay, and this is a huge progress on the black hole information paradox. And you can do it only using this formula. Okay, so using this formula, we can reproduce the page curve. But like I said, this formula can be derived using just the semi-classical gravitational path integral. So in some sense, you can find a result that's compatible with the unitarity of quantum mechanics only using the semi-classics. Okay, so you can reproduce the page curve, which is related to unitarity, and you get unitarity just from semi-classics. And in particular, you don't need the microscopic details of the dual CFT. Okay, so if you would have asked me 5 years ago how I thought the black hole information paradox was resolved, I would have said, oh, well, you probably need to have access to stringy degrees of freedom and branes. And once you know really the full microscopic theory of quantum gravity, then you see that unitarity is restored. And what we seem to find is that actually that's not the case. Just from the semi-classical path integral, we can reproduce a page curve compatible with unitarity.
Alex, can I ask something here?
Yes, please.
So it looks like the result is compatible with unitarity, but it's not quite sure it implies unitarity, right?
Absolutely, that's a great comment. So we haven't shown unitarity. For that, we would really need to show not just that, there's a page curve, but also that the gravitational S matrix maps orthogonal states to orthogonal states. That would be, full unitarity of the S matrix. That has not been done. But so in some sense, this is kind of just one feature of unitarity that we're seeing, but it's a feature that we didn't know how to see before. And that even the feature of the page curve, we might have thought requires you to know about stringy degrees of freedom somehow. So indeed, it's not the full story yet, but it's already a huge leap forward. And it's a leap forward that doesn't require microscopic CFT physics. And I find that both remarkable and puzzling at the same time. And so if you accept this, then there's a natural question to ask is, okay, well, if you don't need all the microscopic details of the CFT, what part of the CFT do you actually need? Okay, and the answer seems to be not all of it. But then what part? And once you've figured out exactly what part of the CFT you need, you can then ask, how does it get reorganized? In this generalized entropy. Okay, this thing is the extremal over gamma of S gen of gamma. Yes, question.
Yeah, so suppose I wanted to compute, say, the Renner entropy of the Hawking radiation. Will this, do you think it will also be carrying out, you can also get it from this semi-classical limit?
The Renner entropies, yes. I think somehow all the eigenvalues of the density matrix you can get this way. But what you will not get is like, matrix elements or operator correlation functions. So somehow there's more information than just what's encoded in the reduced density matrix, or at least in its eigenvalues. There's also, in some sense, the basis of the reduced density matrix, which knows about operator correlations. And that we do not know. So indeed, I think in some sense, there's more than just the page curve, because that's the entanglement entropy. And we also know all the Rennies in principle this way. But there's still more than that. And
yeah, we don't know the basis. That's the whole
exactly. That's how I think about it. We don't know the basis. Yes. Great, thanks. These are great questions. Please keep them flowing. It's much more exciting for everyone that way. Okay, and so I would love to be able to tell you the answer to these questions in a complicated setup like a black hole evaporation or in high energy states, dual to black hole microstates. But I'll have a much more reasonable goal for today and just try to do it in the low energy sector of the field theory, or in the low energy sector of the bulk theory, okay? So for today, I'll try to address these questions in the low energy sector. So without black holes. And as I'll show, actually in that case, we can make this question or this dictionary precise. We can try to make precise exactly which piece of the CFT, how they get reorganized in the generalized entropy. Okay, and that's really going to be the goal for today. But before I get there, I should mention some subtleties. And there's several. The first one is that the entanglement entropy of a CFT, which is a local quantum field theory, this is CFT UV divergent. Okay, just because there's continuous degrees of freedom and very close to the entangling surface, you know, degrees of freedom are strongly entangled. The entanglement entropy in a quantum field theory is a UV divergent object. But this is not really a problem because there's many ways to deal with this, this UV divergence. And there's several other quantities that are very closely connected to entanglement entropy, like, you know, the relative entropy between two states, or differences of entanglement entropy, which is what I'll consider in this talk today, between, say, some excited state and some vacuum. And these objects are UV finite in the CFT. Okay, so it's something to keep in mind, but it's not a big problem because you can just work with other quantities, other observables that are finite. However, there's another issue which is much more conceptually involved, is that there's also bulk UV divergences. And you know, the formula looks like this. There's the area term, and there's the bulk entanglement entropy. But of course, in the bulk, also the entanglement entropy is UV divergence. And so you need to regularize that divergence. And the way that we think about it is really that you know, the bulk divergence is going to be proportional to the area of the bulk entangling surface. In other words, extremal surface. And so the bulk UV divergence will get reabsorbed into the renormalization of Newton's constant. Okay, so the bulk UV divergence gets absorbed in the renormalization of Newton's constant. But then, and the way to think about it is really, you know, the only quantity that makes sense is the combination of these two terms together, because otherwise, if you just talk about one of them, it's not clear what you mean by G Newton if you keep just the area term. And really, once you talk about this object as a quantum object, it's really the combination of these two pieces that is really consistent and can be extracted from the CFT. Okay, and what you can also do is you can run the bulk RG. And by running the bulk RG, one way or another, you can shift contributions between the bulk entanglement entropy to the area term and vice versa. Okay, by cranking up or down the energy scale. Okay, so it's really important here that it's only this combination that makes sense. But right away, once I tell you this, you might be worried, and you might be worried that the program that I'm trying to construct may not make sense, because if I'm trying to attribute, you know, if I'm asking, well, what part of the CFT answer goes into the area term, what part of the CFT answer goes into the bulk entanglement entropy? Well, as I just told you, I can shift contributions from one to the other, and therefore you might think, well, there's going to be no unique answer to the question that you're asking. It's going to depend how much you flowed the bulk RG. Okay, so you might worry that the program doesn't make sense. But what we'll see today is that in fact it does, at least for the types of situations that we'll be considering. And we're going to be able to sort of write down a dictionary that tells us which pieces of the CFT get mapped to what part of the generalized entropy, to the area term, or to the bulk entanglement entropy. Okay, and from the arguments I just gave, this was not obvious at all a priori. So before diving into the precise setup that I'll consider, let me just show you a little bit what this dictionary looks like between bulk quantities and CFT quantities. And of course, I'll have to define the setup where I'm doing it, but I'll do that a little bit later and just give you a sort of summary of results. So there's going to be the CFT answer, and then there's going to be the extremum of the generalized entropy in the bulk. And we're going to expand things, order by order in G Newton, or in CFT language, order by order in the central charge of the CFT. And the first order that will appear is an order, so I'll work in ADS3 CFT2, so we have a central charge C. And the first order that appears is a term that goes like C to the 0, and there's two contributions. There's the identity operator, and there's contributions of double trace operators. And again, if you just bear with me for 5 minutes, I'll tell you exactly how these contributions come about. But I just want to show you what the dictionary looks like, and we'll see that, at the classical level, the identity is completely captured by the area of the classical extremal surface. And on the other hand, the double trace operators are completely captured by the bulk entanglement entropy. Again, for the classical extremal surface. And in fact, the story is slightly more complicated. There's also cancellations happening, as I'll explain, but at a rough level, this is how you should think about it. And this was already worked out in a paper, in the paper with Nabil and Sagar from a few years ago. But what we really did here is we went to order C to the -1, first order in the 1 over C expansion. And this is really the order that's important because this is where quantum extremality kicks in. At first order, the surface doesn't move, and it's really once you go to second order that you can see the quantum extremal surface moving. Okay, and at this order, there's now two operators that contribute, the identity and the stress tensor. And again, these operators get completely captured by the area term in terms of these types of contributions. And there's other corrections appearing at order C to the -1, which are anomalous dimensions and changes in the OPE coefficients of double trace operators. And we don't know exactly yet how these things come about. And what I'll really focus on today is sort of explaining this part of the dictionary. And there's another very interesting question, which I won't talk about at all today, which is asking what happens if your gravitational theory is not just, Einstein gravity or supergravity, but includes stringy corrections. And so in principle, we'd like to understand in the CFT language is what does that map to in terms of 1 over delta gap corrections, where delta gap is the scaling dimensions of operators with spin greater than 2. And this we don't know. This would go a long way into understanding what entanglement is in string theory. And it's a very interesting question, but I won't have anything to say about it today. So my goal for today will really be to tell you, I'll review a little bit how some of this work went, and I'll really tell you about this new entry in the dictionary where quantum extremality is important, and we see the quantum extremal surface moving and how it gets captured by the area operator.
Alex, can
Yes.
I ask something? So,
Yes, please.
So just a clarification question. So this CFT you're talking about is the boundary CFT, not the bulk CFT.
That's right. Yes.
Okay.
Yes.
Okay.
This is the CFT on the boundary. Absolutely. So we're trying to understand, how do certain contributions that appear in the CFT entanglement entropy, how do they get reorganized into A over 4G plus S bulk? And so you can sort of, what I'll show is that you can directly associate certain contributions to the CFT entanglement entropy to particular pieces. Great, thanks. So this is sort of the summary of results, which is a bit abstract for now because I didn't really tell you exactly what the setup is. But before I get started, are there any questions? Great. If not, let me get started. So let me start with the CFT calculation, which will also specify the setup. So I'm going to consider a 2D CFT, a 2D holographic CFT. And the state I'll be interested in, like I said, I'm going to look at only the low energy sector of the theory, will be given by a primary state acting on the vacuum. And this primary state is going to be a single trace operator of the CFT, which corresponds to, which is dual to some propagating field in the bulk. And then the region A of, I'm going to put my 2D CFT on a circle of length 2 pi. And then the region that I'll consider in the CFT, the region A is going to be the interval that goes from 0 to theta. Okay, and theta is allowed to be between 0 and 2 pi. Okay, so we have some CFT on the circle. We take a fraction of the circle specified by theta. We're in some excited state where we inserted a local operator at the origin. And now we want to ask, what is the entanglement entropy in that state? Okay, and people have computed entanglement entropy in excited states in 2D CFTs for a very long time. And it turns out that there's a very nice formula for the Rényi entropies. Where if you compute the difference in Rényi entropies, which is a UV finite quantity now, between the excited state and the vacuum, you get the following formula. So there's many different ways to obtain this that I will not review because they're not particularly relevant for the talk. But you get basically some factors times a 2 endpoint correlation function of the operator O that you started with to create the state. And you can sort of roughly understand how this comes about is that, to create the bra, there's one operator O. To create the ket, there's another operator O. And then when you compute the Rényi entropies, you take n copies of the state. So you're going to have 2 n operators O. Okay, and you work out the details and you get this following thing. And the kinematics of the operators is the following. Here's the complex plane, and here's the unit circle. And the operators are inserted in the following way. So here I would be drawing, say, the 4th Rényi, for example, which would involve 8 operators. And they're distributed on the unit circle. And they're grouped into pairs, if you want. And the distance between 2 operators here is just theta over n, where theta was the size of the interval I started with. Okay, so what's very nice here is that, entanglement entropy is given by a local correlation function with particular kinematics. And of course, a local correlation function, we know how to understand in terms of the microscopic data of the CFT, in terms of local operators and OPE coefficients. And so, this will give us a bridge between the local data of the CFT, and then when we'll try to map it in holography to things like the quantum extremal surface, the area, and the bulk entanglement entropy. Okay?
Sorry, in this
yes.
formula, where are the twist operators?
Oh, the twist operators have disappeared. Very good. So you can think about it the following way. So if you're using twist operators and you're trying to compute, the entanglement entropy, so you can do it the following way. So you want to compute the entanglement entropy on a circle. So the 2 twist operators sit now in the unit circle, and here's the operator that creates the state, which is O to the n. And then there's another operator at infinity, which is O to the n, that creates the ket. And the idea is that you do a uniformization map from this setup to here. Just 2 twist operators you can uniformize to the sphere, to the complex plane, and you arrive precisely at this setup here.
Okay. So instead of twist operators, you get this multiple copies.
Yes, yes. Instead of getting a 4-point function in, say, the orbifold theory, you can uniformize it and get a 2 endpoint function of the original CFT you started with. And in this process, the twist operators have disappeared. And because you subtract out the vacuum.
Okay.
Sorry?
You have uniformized them.
Yeah, you uniformize them. Yeah. And the fact that you subtract out the vacuum entanglement entropy tells you that you don't pick up the UV divergent contributions from the twist operators, basically. So at this stage now, this is just a UV finite quantity. Great, thanks. Another great question. Okay, so of course, what we really want to compute is the entanglement entropy, not the Renyi entropy, which means that we need to analytically continue this object and take the limit as n goes to 1. Okay, and that's difficult because we don't have this formula in a closed form, closed analytic form as a function of n. So that's difficult, but what you could do is you can take a limit where theta goes to 0. That means that the pairs of operators are coming close to one another. And that's an OPE limit. And what you can do is you can expand this answer order by order in the OPE limit, and then it's easy to analytically continue the different pieces. Okay, so that's the strategy. That's the strategy that we did. And I should say that this formula so far is true in any 2D CFT, in the Ising model, in the free boson or whatever. It's true in any 2D CFTs. I haven't used anything about large C or holography so far, but I will now. And what happens in a holographic CFT when you have a 2 endpoint function of single trace operators? Well, to leading order, what you need to do is just compute all the Wick contractions between these operators, because single trace operators are generalized free fields. And so the leading order answer is just given by that. Or said differently, in the OPE language, if you do an OPE expansion, the only operators you need to keep when you take O and O together is, first of all, the identity, and then all the double trace operators. Okay, so you can do that. And to order C to the 0, you get that the difference of entanglement entropy is given by the following thing, and I should put squiddlies because this is an OPE expansion. Oops. And so here's the place where I'm going to start writing down gamma functions without their arguments. And if you get confused, you can ask me, but the following formula applies to the 8H. And here are our gamma functions. Okay, and the arguments of these gamma functions depend on H. It's like, it's like gamma of 3/2 times gamma of 4H divided by gamma of 4H plus 3/2. Okay, so this is the last time where I tell you what they are. And this is the CFT answer. And this first term here just corresponds to the exchange of the identity operator when two O's come together. And the second term comes from the exchange of the operator O squared. Okay, when two operators O come together, they can fuse into a double trace operator O squared. And these are the only two contributions that we kept. And if you go to higher and higher order in theta, you're going to have, the contribution of other types of operators. Great. And so in this paper by Nabil, and maybe I should write it this way. So now let me just add the following term and put again gamma functions here. This time the argument of the gamma functions is slightly different. These times they're arguments of 2H. Okay, so I just added and subtracted two things that are the same. So clearly I didn't change the answer. And when we did in this paper with Nabil and Sagar a few years ago, is show that if you compute, the A over 4G plus the bulk entanglement entropy to this order, you get this, you match the CFT answer, and in the bulk, this thing here is given by A over 4G Newton. And this thing here is given by S bulk. And so, as I said, this tells you that the identity operator is captured by the area, while the double trace operator is captured by S bulk. And the story is a bit more complicated because, in fact, there's also other terms that cancel against each other. And this happens because of a first law of entanglement in the bulk. But still, you match the CFT answer and you can isolate where the pieces come from.
Sorry, maybe it's obvious, but how do you know it's external?
How do you know that
this
this is SPL? Oh, we computed it, and I'll
you-
review. Yeah, so the point is that we computed this and that, and we found this piece and that piece.
and the way you do it is in that you simply compute the graviton.
Yeah, I'll review how we. I'll
Oh,
review
okay.
how we did. Yeah, I'm going to review how we did it in a sec because we're going to need to build on that to go to the next order.
Also, Alex,
yes.
may I ask? So,
oh hi.
Hi, Alex. So I just wanted to ask, can you remind me what was C to the 0 here?
C to the 0 means that these are the terms that are order 1. So
right. So A's bulk is 1 order C less than A over 4G, right?
Very good. So the idea is the following. So yeah, good. So you know, SCFT in the vacuum scales like C, right?
Yeah.
Scales like this, right? But remember that we computed the difference between the entanglement entropy in the excited state and in the vacuum, which means that this term gets killed. And then the A over 4G, because we're considering low energy states that are perturbative, they only change the geometry at order G Newton to the 1 or C to the 0 if you want. So the change in the bulk geometry is not order C, it's order C to the 0. This is different.
Okay. So yeah. We will call the A over 4G as 1 over, order C.
Yeah, so you know,
yes,
if you want so A over 4G is like, you know, A of ADS over 4G Newton, plus if you want like delta A over 4G
okay. Yeah.
And delta A itself is proportional to G Newton. So then you get something that's order 1.
Right. Okay. Mm-hmm. Okay.
Great.
Yeah, thanks. Yeah.
Thanks. These are great questions. Please continue asking them. Okay, so that was sort of the status up to where we were a few years ago. But of course, at this order, the quantum extremal surface doesn't move. It's just fixed to be the classical minimal surface of ADS. And so we wanted to understand what role plays, you know, quantum extremality. So we needed to go to the next order. And so at order C to the -1, you can now compute the change in the CFT entanglement entropy. And you get the following expression. So there's a bunch of different contributions. So let me just write them down. 16h squared, and I'll tell you again exactly where they come from. Theta over 2 to the 4. Plus then there's 24h squared minus 2 delta h over C. And then again, here's the type of things that I don't want to be writing too much in this talk because otherwise I'll never get finished, but let me just start writing them anyway for now, and then we can forget about them. To the 8h, and then here there's some gamma functions. And then again, there's a term like this. And then there's gamma functions. And then here there's Euler functions, which are derivative of gamma functions. Okay, but none of these are just coefficients. They're not functions of theta, they're just coefficients. And they're known, but I don't want to, you can look at the paper if you're really interested, but I don't want to bore you with technical details. It's just what is important is to understand the origin of the different pieces. Okay, good. So what's the origin of the different pieces? There's several. The first, this still comes from the identity operator, but we've defined something which is called delta H here. And delta H is going to be an anomalous dimension for the single trace operator. So what we're saying is that the single trace operator is going to have dimension 2H plus a quantum correction, which is delta H over C. Okay, so if you want, we're scaling that, you know, there's some O with conformal dimension delta, and delta is equal to 2H plus, you know, 2 delta H over C. Okay, and so then the identity contribution gives a 1 over C correction given by this anomalous dimension to the single trace operator. And I'll tell you later why it's important to include something like this. The next term is given by the exchange of the stress tensor. This is the exchange of the stress tensor in the OPE. So the two O's come together, can exchange a stress tensor, and then the OPE coefficient is down by 1/c because the state is light. And so this is the contribution. This term here has, again, this is the contribution of the double trace operator. And so there's the modification of the single trace operator, which also affects the double trace operator. But there's also a new term here. So this comes from what's called gamma NL. These are anomalous dimensions of the double trace operator induced by the exchange of the stress tensor. So for a theory to be crossing invariant, if two operators can fuse to exchange a stress tensor, then it's no longer crossing invariant if you just say that the double trace operator has twice the dimension of the single trace operator. There's a correction that comes due to crossing, and that was worked out in a nice paper by Perlmutter and all. It's fixed, that the anomalous dimension itself is fixed. It's this 24h²/c, but it's non-zero, and you need to include it for the theory to be crossing invariant. Okay, and at the same time, there's also the thing called A and L, or in this case, we're just keeping the 0, 0, 1 of it, which is again, it's not only the anomalous dimension that changes, but also the change in the OPE coefficient between COO². So, COO², the OPE coefficient, generalized free fields tells you that this is 2 or maybe square root of 2 plus a quantum correction, A00/c. Okay, and again, this is fixed for the exchange of a stress tensor. We know what A00 is, and it's this 96h²/c. Okay, so these two terms here are required by crossing. Once you exchange the stress tensor, and every CFT has a stress tensor, so you must exchange the stress tensor, then you also need to correct the double trace data, and you do it in a way that's fixed and is known, but you need to take into account these contributions. Okay, so this is the full answer, and the idea would be to understand how we reproduce this from the bulk and how these different pieces get mapped to S bulk or to A/4G. And we don't have a complete picture yet. We're working on it. It's still work in progress. But what I'll tell you about today is the first line. Okay, so we can go back to my summary. If you remember my summary, I told you that I was going to give you this red box here, which is just the identity plus the stress tensor. And that's the first line in the expression that I just wrote. Okay, so that's what we're going to try to reproduce from the bulk. Good, so this was my part on the CFT calculation. Before I turn to the bulk, are there any questions?
Yeah, so basically, very short again clarification. So you're able to only reproduce order by order in what is called the H-bar expansion in the bulk, right? This is the.
That's right. Yes.
Yes. But this method, you will not automatically see the generalized entropy to all order in H-bar, that you need to see the phase transition in the page curve or something like that.
No, exactly. So this is a more, cautious, a less ambitious goal, which would be to understand what happens in something like the page curve. We already sort of know that for the page curve story, because you're probing properties of black hole microstates. I mean, I think all this work on wormholes and ETH, and what I would have talked about if I didn't talk about this paper, would be to say that, there it's sort of statistical properties of the OPE coefficients and the spectrum that are important to get the page curve. So here we're less ambitious. We're not trying to talk about properties of black hole microstates. You see, this only involves operators of very low dimension. But the nice part is here we can do it exactly. Here we're not saying anything statistical. Here, these are all well-defined numbers, order 1 numbers, and we have to match them between the bulk and between the CFT. So this is what I meant by precise. Here we can really build a dictionary that tells you, like this piece equals that. And what we think will happen for high energy states is probably, this piece of the bulk is captured by statistical average over this piece of the CFT, maybe something like that. But again, studying black hole evaporation or black hole microstates goes beyond the goal of what I want to discuss today.
Okay.
Yeah, thanks. Good. Any other questions, or should I jump to the bulk? Okay, let me go ahead. So the bulk calculation. My pen is not working very well. Well, I hope this gets better because it's going to be annoying. Okay, so remember I told you that the CFT state was given by a local operator, a local single trace operator acting on the vacuum. And so you can ask, well, what is the dual state of the bulk theory? And because in the bulk, the operator O is dual to some scalar field phi, the bulk state is easy to identify. It's just that, the bulk field phi can be expanded in creation and annihilation mode. It's free field theory in ADS. And the bulk state is just a one particle state where you act with, the lowest mode number, A00 dagger, acting on the vacuum, on the bulk vacuum. Okay, so this is the state of the bulk theory. A single trace operator acting on the vacuum is dual to one particle state of the bulk theory. Right, and of course, if I had created a state in the CFT by acting with a double trace operator on the bulk vacuum, I would have obtained a two particle state of the bulk theory, and so on and so forth. Okay, so what happens at order G Newton to the 0? There's two effects. The first one is that the geometry changes. And so, once you're in this excited bulk state, psi bulk, and you compute the expectation value of the bulk stress tensor, I'm putting bulk everywhere so that we don't get confused with CFT, this is no longer 0. Right, the expectation value of the stress tensor in a one particle state is not 0. It's 0 only in the vacuum. And for example, if you look at the energy or the energy density T00, and you look at what the expectation value of T0 looks like in this state, there's some lump of energy sitting at the center of ADS that decays. Okay, and how far out this goes as a function of R is basically determined by the conformal dimension. Okay, and the heavier, the more massive the particle is, the more it's localized at the center of ADS, and so this is like the constant wavelength of the particle. But once the stress tensor is no longer 0, we have to remember that there's a theory of gravity living in the bulk, so we need to go and solve Einstein's equation. So there's a non-trivial equation to solve, which says that the Einstein tensor is given by the expectation value of the bulk stress tensor. And you can do this. You can find this geometry exactly. We did it in this paper with Nabil and Sagar, and you get a geometry that looks like a regularized version of a conical defect. A conical defect is kind of like the limit h goes to infinity of this thing, where the particle becomes so massive that it's no longer spread by its wavelength. But at finite h, or for h of order 1, it's kind of like a regularized version of a conical defect. Okay. So you solve this equation. We can do it explicitly. I don't think I'm going to write it down because in the essence of time, it's not really useful. So you find a new geometry. So, G mu nu is equal to G mu nu of ADS plus a first order correction. These are simple functions of R. They preserve spherical symmetry. They're easy to find. And so you can find this geometry, which you can also think about as the gravitational dressing of the one particle state. Okay, and then you can compute the area on this new geometry, but there's no need to find how the surface moves. So, you could you could say, well, maybe the surface is given by the classical extremal surface of ADS plus a first order correction, but you don't need to find this first order correction because the surface is extremal. Any first order change in the geometry will not make gamma 1 move by extremality. Okay, so you don't need to look for another surface. You can just compute the area of the old surface on the new geometry. This is pretty typical with like first order variations. That's the first effect. The second effect is that the new state polarizes the entanglement. So this state polarizes the entanglement. And the easiest way to see that is the following. You can rewrite, so A dagger is a mode of global ADS, but you can rewrite it in Rindler space as being given by, Bogoliubov coefficient times the Rindler modes. And then, the vacuum state would just be mapped if you take the vacuum state and trace over the left Rindler ADS wedge, you would just get a thermal density matrix. But now, because you have A daggers here, you just get a modified, so we could let's call this operator O or something. You just get the following state in Rindler space. So it's like it's not quite the thermal state, it's some modification of the thermal state where you act with this particular combination of Rindler modes. And this is an explicit bulk density matrix. You can go and compute the bulk entanglement entropy, which we did. And what we did is, we computed the bulk entanglement entropy between this excited state minus the bulk entanglement entropy of the ADS vacuum. And this is a quantity that you can compute and check is bulk UV finite. Okay, because just like a difference in entanglement entropy in the CFT was UV finite, a difference of entanglement entropies here is also UV finite. And I should have maybe said, but the area is bulk IR finite because we're looking at the difference between the area of ADS and the area of this modified state, which means that the answer is also CFT UV finite. Okay, so at this stage, all possible types of UV divergences are just killed by these differences that we're considering, and we just get finite quantities. And as I said, maybe I'll rewrite it. So you compute the expectation value of the area operator in this state minus that of the vacuum. And you get the following expression. This is what I wrote on some previous page. Theta over 2 times these gamma functions. And then you compute S bulk minus S bulk exciting minus S bulk of the vacuum. And you get this other term times the gamma functions minus sine of theta over 2 to the 8h times other gamma functions. And like I said, these terms cancel against each other. They cancel because of a bulk first law of entanglement. And you're just left with this, which was exactly the CFT answer that I wrote on the previous page or 2 pages ago. Okay, so this is the computation that we did back then with Nabil and Sagar, but now we need to do more. We need to go to the next subleading order where quantum extremality is important, and in particular where the change in the surface will be important. Okay, so now we have to ask what happens at order G Newton to the 1. So, what we should do is expand the metric, saying that it's the ADS metric plus G Newton times the first order correction, which I just told you how to compute, plus G Newton squared times a second order correction. And then likewise, the location of the extremal surface, gamma, should be expanded to be the ADS answer. Plus G Newton times a first order correction to gamma, plus G Newton squared times a second order correction to gamma. And of course, this goes on, so on and so on. So if you ask at second order in gamma, what are the important terms that contribute to the area operator, you find the following terms. So like this is order, G Newton to the 1. You'll get the area of the classical extremal surface, but evaluated on the second order geometry. You'll also get a piece which comes from in some sense, the location moving to order squared on the background geometry. Plus, you'll get a term which moves, which computes the first order corrections to the metric squared times 4 GU. Okay, and you can ask why I didn't write a term that looks the following. Sorry, there's another term that I didn't write, which is the first order. Sorry? Was there a question?
I was just saying gamma 1 G1, nothing.
Yeah, gamma 1 G1. Thank you. Right, and there's another term that I'm not going to write, which is a term which is gamma 2 G0, because again, this term looks exactly like what you would have written at first order, which would have been a gamma 1 G0 term, but by classical extremality of the surface, because the surface is extremal, first order variations don't matter. So if you're just evaluating it on the background geometry and perturbing the surface linearly, in this case, linearly in the parameter G Newton squared, this term by extremality cannot contribute. Okay, so we have these 4 terms to compute, and it's pretty clear what's needed. So this particular term we already have, because G1 we already know from the first order computation, but it's clear what the two new data, what the new data is that we need. We need the second order correction to the metric, and we need to know how the surface moves. Okay, so this is what we need to find.
Alex, one question here. So probably you're going to already say this. So when you do the bulk computation, you don't find any renormalization of the Newton's constant that you need to take into account?
No, so this is a little bit the miracle of computing a bulk. The difference also in the bulk is that it happens that the difference of entanglement entropies is UV finite in the bulk. At least, to order G Newton to the 0.
Yeah, so maybe it's a stupid question. Then how do you match this two from the CFT and the bulk Newton's constant? What exactly? Because there you have a running of the Newton's constant in a way. Only the full answer makes physical sense, and here the Newton's constant is not running. So how do you match the two?
I think I would say it slightly differently. I would say that here Newton's constant is also running. But it so happens that the quantity that you compute is not sensitive to the running. So, because you're computing differences of entanglement entropy, there's no UV
okay, there's no state dependence. There's no state dependence in this.
Yeah, exactly. If I had computed just S bulk excited, there would have been a divergent piece that needs to be renormalized and absorbed into G Newton. But because I'm subtracting the vacuum, that goes away. And so in some sense, there's nothing left to be absorbed. So if you want, and it's the same thing in the area operator. If you look at this term, the idea is that you could have renormalized G Newton here, but the difference is not sensitive to how you renormalize G Newton. At this order in the expansion.
Okay. Yeah, I'm just trying to understand just from the CFT point of view, what's that physical GN that we should be identifying with the bulk theory?
Yeah, so in general, we write that the central charge is 3 LADS over 2 G Newton, but this is really 2 G Newton bare. And in principle, this can have some corrections, right? And I think the idea here is that these corrections may exist. And in fact, the paper that we wrote with Nabil and Yorit, what we did is we computed these corrections for the graviton entanglement entropy and the photon entanglement entropy. It's a bit harder to do for the scalar. But the idea is that, whatever you put here, it will not affect differences, basically.
Okay, thanks.
Because it's going to be, they're going to appear with the same coefficient. And so at the end of the day, it disappears in the difference. Now, this was a statement to order G Newton to the 0. This is an important question. It's not completely clear that once we go to order G Newton to the 1, we all always, even in differences, we have UV finite things. I think that we still don't fully understand yet. And like I said, today I'm going to talk about the area operator, not about the bulk entanglement entropy. And so you might worry that, you know, in the bulk entanglement entropy, there's going to be UV divergences that you need to renormalize, and that even in differences, you cannot get away with having to see these terms. We don't.
The identification with the central charge should not be state dependent, right? I mean.
Yes, exactly. That's right. Yes. I agree.
Okay.
Yeah. Very good. Thanks. Okay. So the question is now how to find G2 and gamma 1. And G2, we know what the prescription is. So remember, we have ADS, we solve the Klein-Gordon equation, we find the mode function, we construct the one particle state. Then the stress tensor is non-trivial in the one particle state, so we have to back react. At the next order, it's obvious what you need to do. You need to solve the Klein-Gordon equation on this back reacted geometry, find the new modes with their wave functions, excite the one particle state, compute the stress tensor for that, and back react a second time. Okay, and so that's conceptually that's straightforward, but in practice it's kind of hard, and this is where really Sean did an amazing job at computing these wave functions. And so, you know, the classical wave function is very easy. It's just the wave function of the primary state around the ADS vacuum. And then there's a correction function, which maybe I'll call F1 of R. But we were able to find this function analytically. It's some complicated hypergeometric mess, but it's a function that we know analytically. And once you have that function, then you compute the stress tensor. So you can ask what it looks like near the boundary, and near the boundary. So it looks like, you know, this just becomes 1 over R to the 2H. This is the usual relation that you know from ADS-CFT. But the quantum correction involves the R to the 6H term. And again, the 6H term you can understand because, you know, we squared the wave function to compute the stress tensor. So we had an R to the 4H in the stress tensor that we back reacted on the geometry, and now we resolved the equations of motion. So in some sense, that's why there's a R to the 4H difference between the leading term and the back reacted term. Okay, and then so you have this wave function, you compute, you know, now you go and solve G mu nu second order is 8 pi G of this thing now on the back reacted spacetime. And it turns out that you can find G2. And again, G2 is a very complicated function, but a function that we know analytically. You actually can solve this differential equation analytically. It's even worse than the mode function, but we know it. Okay? And so this you should think about as like a second order gravitational dressing. But you find the function, and again, it's a regularized version of a conical geometry, this time sort of back reacted to second order. Okay, so it's smooth as R goes to 0. It has some profile like this, and it has some leading order profile and some G-nun corrections to it. But you can you can find this metric explicitly, and then you can just compute the area operator. Okay, so you can compute this piece G2 over 4 G-nun, and there's many terms. There's a theta squared term. Then there's corrections that go like theta to the 4, and then there's theta to the 4H pieces and theta to the 8H pieces. Okay, it's some kind of complicated mess. But we find an explicit expression, and then you can start asking how that's gonna match with the CFT. And there's one important thing to keep in mind here is that we need to make sure that we're specifying the state the right way. And so one thing that you need to check is what is the bulk energy of the state that we have. And so you can compute that using, you know, you compute the ADM mass. And you find that in fact, the ADM mass is not just 2H like you had for the classical state, but that there's a correction now from the second order back reacted metric that is different and is given by the following expression. And now I'm also using the relations that I know between LADS and G-nu. And so what this tells you is that the energy in the one particle state is no longer just the classical scaling dimension of the operator, but it picks up a correction piece. And so the interpretation for this piece is that this is the anomalous dimension of the single trace operator. Okay. And so for you to build your dictionary between bulk and boundary in a consistent way, you need to take into account the fact that there's this anomalous dimension of the single trace operator. Okay, so that's one thing to keep in mind. But once you keep that in mind, basically you're good to go. And all you need to do is ask how to find now the change in the extremal surface. And I see that I'm slightly running out of time, so I'll try to just make this quick, but I'll sketch how you find it. So the idea is that you go to Rindler coordinates. And then, in Rindler coordinates, so the metric is and in these coordinates, the entangling surface is just rho equals 0. And of course, there's a correction, there's the first order correction to the metric, which gets mapped also to Rindler coordinates. So the classical surface is just rho equals to 0, and the quantum extremal surface is given by, rho equals 0 plus g nun times rho 1 of x. Okay, that in rho 1 of x parameterizes along the horizon or along the quantum extremal surface, how the surface moves. And then you can go and compute the location of the surface. So, in some sense, a over 4g nun of rho is 1 over 4g Newton integral dx. Now I'm just writing the definition for the surface, rho prime plus g rho double prime. And you expand this out, and then you just basically get, like this becomes a classical mechanics problem where you have some Lagrangian and you need to find the location of the surface rho of x. And what happens is that this correction to the geometry, it contributes a potential term. It contributes a potential term in the geometry. So roughly speaking, the equation of motion for the location of the surface is just something like this: rho prime of x minus rho of x plus a potential equals 0. And here, this potential is really coming from the first order change in the metric. But of course, the question you should ask is: this is a quantum extremal surface. We're supposed to be extremizing not just a over 4g, but a over 4g plus s bulk, right? And s bulk depends explicitly on the location of the surface. So why did I not write s bulk here? And the point is that s bulk, you can take it into account, but s bulk itself only contributes a potential term. So maybe I'll write it this way. So if you take into account the bulk entanglement entropy, you get also a correction. But the correction is such that it just contributes a different potential term. And this differential equation has a homogeneous solution plus corrections coming from the inhomogeneous piece, which is this potential or this source. But you can treat these inhomogeneous pieces just independently, separately. So in some sense, you can isolate the contribution just coming from this piece here. It doesn't mean that it's the full answer to S bulk, but it means that it's the part of the full answer to A over 4G or to gamma 1, but it's the part of gamma 1 that only knows about the change in the bulk geometry and doesn't care about the bulk entanglement entropy. And you can do this really because of this sort of factorizing property, if you want, between the potential terms. And the idea is that if you take this into account, you can go ahead and compute the location of gamma 1. So it's not the full gamma 1 because of this. So maybe I'll call it gamma 1 geometric. Okay. and you find the location of the surface, and now you can compute the, this term, which was gamma 1 G1 and gamma 1 squared. Okay, you can compute both of them. So we have this, we have G2. You put everything together, you do a lot of very, very complicated integrals. And what do you find? You find that 1 over 4 G Newton, psi A psi, again, to order G Newton to the 1, is equal to the following expression, 2 delta H over C plus theta to the 4 over 360 minus 16H squared over 15C, theta to the 4th over 16. Okay, and this is what you get from the bulk after using, again, the relation between delta H and using this bulk energy correction, which specifies what delta H is. So this thing becomes delta H. So once you know that, you use delta H here, and you use the relation between G Newton and the central charge, and you get this final answer. And now you can ask, how does this final answer compare to the CFT contribution? And it turns out that it's exactly the expansion of the CFT contribution to that order. And you can check higher order terms as well. So basically, we've reproduced the first line of the CFT answer. Okay, so the statement is that by keeping, if you want, the second order geometry and only the geometric piece of the quantum extremal surface, we're capable of reproducing the exchange of the identity operator and of the stress tensor. And of course, that's not the full CFT answer. You also need to compute the non-geometric piece, the gamma 1, and also compute actually the bulk entanglement entropy. And the idea is that that will give us the other pieces in this table, which are the anomalous dimensions and the change in the OP coefficient.
So essentially, you're able to reproduce the gravitational dressing by taking the contribution of the identity block and tensor explicitly. Is this a correct way to summarize?
Yes, yes. Although at this stage, it's not the 0-0 identity block, it's more like just the global block of the stress
global
tensor.
Block, yeah.
Because the 0-0 identity block would would have multi-gravitons. So these would also contribute, but at higher and higher order in the 1/c expansion.
Exactly.
And I think because it worked this way for the first two orders, it's not crazy to conjecture that maybe the 0-0 identity block is completely captured by the area operator. And that the bulk entanglement entropy is somehow completely captured by the multi-trace operators. And of course, there's going to be, just like already we saw the classical order or the first non-trivial order, there's already going to be cancellations between the two. But these cancellations, you don't really see them in the CFT, and that the pieces that you do see contribute solely to the area operator for the identity block and solely to the bulk entanglement entropy for the multi-trace operators. But that's a conjecture, and it would be very nice to check. So just to summarize, the idea here was to try to build a dictionary between the microscopic building blocks of a holographic CFT, which are the scaling dimensions of the local operators and their OPE coefficients, and geometric objects, which are quantum extremal surfaces, which is made of an area piece and of a bulk entanglement entropy piece. And what I showed you today is up to the order c to the -1, or second non-trivial order in the back reaction or in the quantumness. It seems that the contribution of the identity operator and the stress tensor global block are fully captured by the bulk area operator. And this is really an order where quantum extremality is important and where we see the surface moving. So it's pretty exciting. And of course, what we're working on right now is to try to understand how the bulk entanglement entropy pieces can be calculated, and whether they're UV finite or not in the bulk, and all this kind of stuff. But anyway, I'm already quite a few minutes over time, so let me stop here and thank you for your attention.
Yeah, thanks for this wonderful talk. It was very interesting. So time for questions. Okay, let me already ask something. I hope others will also ask soon. So if you want to carry on this program at higher orders, and let us say that we put a delta gap to infinity, So in all of these computations, it seems that all the things that you require are the central charge being large and the spectrum is sparse. Like you have only taken only a few single trace and the multi-trace operators built out of those. So now, do you think at some level you might be able to see for the consistency you should have some specific constraints on the 3-point functions and some other stuff, like for this interpretation to hold as a surface?
That's a great question. I think probably the answer to that, at least the naive answer to that, is no, because what I would say is here, how does this work? You write down some EFT in the bulk, or you think about some CFT data. You write down some CFT data that's crossing invariant in a 1/n expansion. You pick the number of single trace operators that you want. They have certain conformal dimensions. Like you pick all of that, and that specifies a bulk EFT. And then you compute things on both sides and match them. And naively, it seems like you could do that for any EFT and not that it's blind to any types of constraints. Now, of course, quantum information measures like relative entropies, they have constraints, right? Like there's the positivity of relative entropy and that kind of stuff. And so you can ask whether or not you can use this type of technology to constrain bulk EFTs. And probably to some extent, the answer to that is yes, but I think in the sort of primitive way that we're doing here, where we're just trying to build the dictionary, you won't be able to see that. To see any kinds of constraints, you need to do something different and really, I don't know, try to construct some relative entropies where maybe if you pick a funky bulk EFT, they can become negative at some point or something like that. But I would say sort of, if you just take the setup, what I discussed today and try to generalize it to all orders, I don't expect you to be able to rule out EFTs that way. That has to come from some new input.
I see.
It's an interesting question.
But as you said, that it's not that obvious that we could always, if you're, I would be very happy to see an all order statement. Then
yes,
that would be awesome. Yeah, I understand it's very hard, but
yeah, I think to be honest, even this calculation at second order is. Well, first of all, it's just technically difficult because you have ugly integrals to compute, but that's just technical. It's also conceptually very difficult to understand exactly what's the right thing to do. And part of the motivation for doing this is also trying to, there's all these nice generalized entropy statements, but what does it really mean? When you go and now specify the bulk theory, what are you supposed to compute? And for example, in nothing in the talk that I discussed today, I said anything about the entanglement entropy of gravitons, right? Now, we worried about this question just in the vacuum, understanding the entanglement entropy of boundary gravitons in the vacuum, and we got some answers where just the central charge was being renormalized. But you can ask, once you go to subleading orders in 1/c, where the different fields are interacting, why did I not have to take into account the entanglement entropy of boundary gravitons here? It's not obvious that it cancels between the vacuum and this state because this state is excited and the excited states talk to the graviton at order 1/c. It appears that we match the CFT answer without using them. So it seems, and the boundary gravitons you might think are associated to even powers of thetas here because they're kind of like the stress tensor, which has only even powers. So it seems that somehow we don't need boundary gravitons, but to be honest, I'm not exactly sure why. It's more of what seems to come out.
Interesting. I see. Okay. Very nice. More questions? Okay, maybe I have a short question also to end. So there was a computation by Faulkner, which was similar in kind of spirit, although very different computation. So he was, I think, just simply trying to understand how the entanglement entropy flows with RG flow. Like he was taking a relevant deformation of the CFT. And then he was able to show that if you do the computation, in the CFT, the bulk geometry also emerges from the computation in a very natural way. And are you aware of this work?
Yes, I think I know the papers you're talking about. Yes.
So I was thinking, is it yeah, I was always, whenever I read it, I thought that maybe it's also useful to understand it from the point of view of the quantum extremality, if that can has a way to because yeah, because the one nice thing I found about that computation is that that there was no separate computation that was needed to do it. The CFT computation itself became a bulk computation in a natural way. I think that was a nice point
And
of that.
do you remember what was controlling classicality in that setup, right? Because
No, I don't.
I think there's many contexts in ADS CFT where we have sort of seen, auxiliary ADS spaces emerge, or, asymptotically ADS spaces emerge. Because in some sense, it's just a way to realize conformal symmetry, or, if it's only asymptotically ADS, like a flow away from conformal symmetry. But to really, have a classical bulk and be able to separate between.
No, actually what I think this was a little bit more than that. He was even seeing the emergence of the bulk field, and he could reproduce the CFT computation by this auxiliary bulk field. And the reason a bulk field emerged because of this deformation parameter, because you had a RG flow. I think it was the large C limit, but
I see. It was like a RG flow of a large CFT.
Yeah, exactly. So I think it was not a very contrived computation in the sense that it came out naturally.
I see. Yeah, so I don't remember exactly what they did. I know Tom had another paper with Cesar Agon where they computed. This was the first paper that really tested the FLM formula, where they took two spheres in higher dimensions, send them very far away, and compute the mutual information, and do it at the quantum level in the bulk field. So they assumed again that the OP is dominated by a double trace operator, and then they did a computation in the bulk. And that's a bit similar in spirit to what we did with Nabil and Sagar in the first paper. And I don't think they ever tried to do 1/c corrections there where the surface moves. And that I think that would probably in their kinematics be very, very hard. Somehow the nicer thing with these, with doing a single, so their thing is more like two intervals. The nice thing with doing one interval but an excited state is that you have a bit more control. But yeah, these are interesting questions.
Okay. So thanks again. Oh, okay.
Yeah, no, I don't actually have any questions. So thanks, Alex, for the nice talk. But do you have some time, Alex?
To stay?
Yes.
Yes, I have time.
We could end this recording and we can have an informal chat. Yeah.
Yes.
Okay. So
that would be great.
So let's end the recording now. Let me put here.